everybody, and welcome again to my home. I am Patrick Rowley from the James E. Richmond Science Center for another episode of our Science on the Sphere at Home. I'll be using the SOS-X, or Science on the Sphere Explorer app from NOAA, the National Oceanic and Atmospheric Administration. It's an app that you can get for your phone or your tablet. And it's a way to look at global data on a sphere, on your own portable screen. We have a Science on the Sphere at our Science Center. It's a huge 6-foot globe suspended from the ceiling. Unfortunately, I can't bring one of those into my apartment here. So here we are with the SOS-X app. Now, we've spent the past few weeks looking at all types of different data here on the SOS-X app. This week, we'll kind of put some of that together and look at some climate change data, starting here with a temperature anomaly data set. Now, what does that mean? Well, I'll tell you. So I'm going to bring up this screen a little bigger for you so that you can see. All right, so here we go. And what we're looking at here again is temperature anomaly. Now, let me back this up and explain what that means. So we're back looking at around the year 1800. Right? So we've backed up that time period here. And what this is doing is merging land and ocean temperature, surface temperature data from thousands of land and ocean temperature stations. Okay? It's data that is from the Climatic Data Center, National Climatic Data Center from NOAA. And it shows anomalies, meaning that where we have blue on here, and the more blue it is, it means it is colder than the 100-year an average, all right? Where it's red and deeper red, it means it's that much warmer than the average temperature. And where it's kind of white in the middle, that means it's pretty close to average. So this is kind of showing us that data over a certain time period. And we can see some reds, we see some blues throughout the time here. If I spin the world around, we can look over here in Asia, and you'll see that there are years where it seems to be more warm, years that it seems to be cooler. But if we fast forward this to now, you'll notice that now we're around 2010, 2011, that a lot more of these years are a deep, deep red, showing that it is warmer. Some years are still pretty cold compared to average, and that might be in one place where it's very warm in another part of the world. All right, so we're back in the 1800s. Let's go again to the current temperatures. All right, so this is back in 2001. So what's interesting is this data set happens to go through 2017, it goes through 2019, I believe, on the Sphere at the Science Center. That 2016 is the warmest year on record since 1880. 2019, last year, was the second hottest. And the five past years, starting 2019 back 5 years, are the 5 hottest on record. All right, so just kind of put that into perspective for you as well. You'll just kind of see in general here, in these early years, there's a lot more of the blues and the reds are not as deep. Whereas when we go forward, closer to now, just look at that's 2007. You'll see a lot more of the reds, all right, kind of taking up more of the globe, okay? Now, moving on to our next data set here. We're going to be looking at the carbon dioxide concentration. Now, this is a model from NASA. It's a computer model called GEOS-5, and it was created by the Global Modeling and Assimilation Office at NASA's Goddard Space Flight Center. And it's a model, all right? And so what it's showing is the areas where we have high concentrations of carbon dioxide. But what's really kind of key here is to see how the weather patterns influence where that carbon dioxide concentration moves towards. If we look over North America here, you can really see how we have these areas where of high concentration in the Midwest, along the East Coast, where we have a lot of emissions, right? But then the weather pattern kind of carries that off into the Atlantic Ocean, so to places that didn't produce that carbon dioxide or emit that carbon dioxide, but it is being transferred globally. If we look over here in Asia, again, another area where we have a lot of carbon dioxide emissions, right? And what's interesting is you'll notice right in here, it's like this pocket where there's none, all right? You have the Himalayan mountains here, to the Tibetan plateau, so you're at a high elevation, and the winds are basically moving around that area, so the carbon dioxide does the same thing. So it's kind of this dome or shield where we don't have as much. Also, if we look in Africa, there's a little bit in the south there, there we go, right in that southern part here. All right, and that's from some wildfires that were happening at the time. So not a man-made cause of carbon dioxide, but a natural cause. And we can still see how that was impacted by the wind patterns moving it away. All right, now we're going to look at one. We may have looked at this earlier a few weeks ago, but this is looking at sea ice concentrations, but only for September. So every year we have September, kind of early to mid-September, we have what's known as the Arctic sea ice minimum, kind of at the end of the season of melting through the northern hemisphere summer. And so what this does is show us how much warmer essentially that year was by how much ice had been melted, all right? So this goes back to 1987, and we're currently in 1996. You can see that for the most part, each year at the minimum looks pretty similar. There's some reduction because it's the end of summer. But as we go forward in time, we get that minimum starts getting smaller and smaller, all right? So we're at 2002 now. If we fast forward this to 2008, for example, or 2007, 11, 12, look how much smaller the ice is in these areas. You can go forward some more, 14, 15, 15, a lot smaller than it was back in 1987 for the same time of year, all right? We can fast forward this. I think it goes all the way up to 2018 as well. So smaller there as well, okay? So now I'm going to finish up with a little Science on the Sphere movie that kind of summarizes all of what we've talked about here. And it is called Hot Air, Atmosphere and Climate Change. And it's from Science Museum of Minnesota. They have a Science on the Sphere there as well.
The biggest impact that humans have had on the atmosphere is the burning of fossil fuels. And this is having an effect on the Earth's climate and will continue to have an effect into the future. I studied the part of the atmosphere closest to the ground because that's where we live. And that's where interesting things are happening. The more carbon dioxide molecules in the atmosphere, the more heat they're going to absorb and emit. Think about a room with a few people in it and pretend those people are carbon dioxide molecules. If you were to add more and more people to the room, those people are going to give off more heat, and the temperature of the room is going to increase. We have increased our carbon dioxide concentration in the atmosphere from nearly 300 parts per million to 400 parts per million in only 200 years. The last time that the Earth had this concentration of carbon dioxide, humans didn't exist on the planet. And so we really have no model for what that amount of carbon dioxide is going to do to us trying to live on Earth. Take a look at this data set. This data set is showing temperature departures from normal over the period 1880 to 2012. If there was normal ebb and flow of temperatures, you'd see a mix of red and blue over the 128 years. But that's not what happens. Instead, what you see is that it was cooler earlier, and now all the warmest years are concentrated in the last 20 years. It's gotten a lot warmer, and it's staying that way. Temperature affects where rain falls. So we're not only concerned about an increase in Earth's average temperature, but we're concerned about what this means for rainfall patterns. I study urban areas and how heat and rising temperatures affect them. Cities are already warmer than rural areas because of all the concrete and asphalt, the way cities are built and work. We call this the urban heat island effect. I've been studying cities around the world to compare how cities differ in the way they warm. Some cities are closer to water, some cities have more vegetation. By comparing these different cities and their characteristics, I'm hoping to understand how we can cool cities and lessen the warming that comes from urban heat islands. There's so much we don't know, but there is one thing we do know. The warming that is happening in cities and all around the globe is going to stay with us for a long time because the carbon dioxide is going to stay with us. So we need to figure out the best ways to deal with that.
And that's all I've got for you this week. We'll be having, I think, one more episode next week to look at some of my favorite things here on the SOSX. Maybe even some new cool things that you can't do on the Science on the Sphere. So stay tuned for tomorrow. We'll be publishing a whole lot more of our Science at Home activities on our website, Facebook, and Twitter. Until then, have a good weekend.